What's up, Honors Algebra 2? How you doing? We're going to do some transformations today of what I like to call creature graphs. So here's a little example, just this little squiggle here. It's something I invented. We don't need to worry about the equation, but we do have to recognize, okay, for this one problem, this is f of x. And what we've got to do is decode this new transformation, f of x plus 1 minus 4, and figure out what the graph of that looks like. So we've got two choices. We could either do the computations or the transformations on the table of values that you see on your paper, or we can move the points manually. Some of you will gravitate towards one method, some of you will gravitate towards another. If we do decode the transformations, I've written some of them out already, and you might find it's easier to pause the video here and there. But we will decode the plus 1 inside as a left 1 and the minus 4 outside as a down 4. Now, if you think of what happens to the values, if you move an x value left by 1, let's just take this x value here, this random point, its x value is 1. If we slide it left 1, we are decreasing it by 1. So to transform any x value to the left, you decrease it by 1. And to transform any y value down by 4, you subtract 4. So if we do these computations on the actual numbers in the chart, I've taken the original 4 points that make up this little random squiggle. I subtracted 1 from all of the x values, and here's where they are. And then I subtracted 4 from all of the y values, and here they are. I'm telling you, my friends, if you now plot these 4 points, what you're going to see, we do see that new squiggle has been moved in its new home. So if you don't mind doing a little computation on these ordered pairs, you can do the transformations that way and then plot them. If you prefer option number 2, move the points manually, maybe some of you will, I would just say your job then is to take each individual point, say for example this one, and move it left 1 and down by 4. And you do see it lands exactly where we thought. And if you carry that through the rest of the 3 points, you will get the same shape. So let's keep trying this, and hopefully by the 5th one, you're all set to go. As we look at number 2, I've done some pre-writing already, but I want to remind you we do reflect and dilate before doing any slides. It doesn't matter if you dilate and then reflect or reflect and then dilate. That doesn't matter. But anything multiplied, whether it's a negative or a value, that always happens before the slides, which are adding and subtracting. Let's decode the transformations here. We've got a negative. It is multiplied outside of the function. Outside is vertical. That will be a reflection over the x-axis. And then we'll move everything down by 3. So let's think about what would happen to the y values. If we reflect any point over the x-axis, what actually happens is the y value changes sign. I'll show you right here what I mean. For example, if we were to take this 1 point and reflect it over the x-axis, it would mirror image appear down here. Now, the x value is the same, but the y value did, as you can see, change signs to accomplish that reflection. So that operation happens first. Then we want to move everything down 3. That's going to decrease the y values by 3. Both of these transformations are vertical. That means the x values that we started with are going to be the exact same x values that we have on our transformed shape. But the y values, my friends, we've got 2 things to do. First, multiply each of these by -1 and then subtract 3. So for example, -1 times -1 is +1, and then we subtract 3. That gets us a -2. If we continue that for the rest of the y values, there we have it. And if I plot these new points, let's see, 4, -2, 0, -3, 1, -4, and 3, -4. I get this guy here. I don't know. Looks pretty cool to me. And we can visually confirm, yes, this really does look like I took this starting creature, flipped it over the x-axis, and then moved it down by 3. So always remember your two options. I showed you transforming the points, but now I'll just run you through one instance of transforming the points themselves on the graph. So I'll continue with this one. We'll track where it goes. Let's do a reflection over the y first. That would temporarily move this right here, as we've already discussed. And then we would move it down 3 more places. And you see, it aligns exactly the way we thought. If you do that a couple more times for the next random points on here, you'd see they align as well. Okay, let's keep going. I'm going to just get the new page here. Here we go. Oh, let's see. Is the video still going? Yes, it is. All right, we're good to go. Sorry. Now, number 3. We've got a couple operations to talk about here, but I'll keep reminding you, reflect and dilate before the slides. So if we decode this transformation, we've got a negative, a 1/2 multiplied. Remember, treat the negative separately from the 1/2. So our negative would actually be a horizontal, the negative, would be a reflection over the y-axis. The 1/2 inside, we'd divide all of our x values by 2. We'd call that a horizontal expansion by 2. Both of those affect the x values, so we'd multiply all the x values by a negative for the reflection and by a 2 for the expansion. So that's what's going to happen to all the x values. We're going to multiply them by -2. Then we have this up 3. That'll just increase all of the y values by 3. So let's do some math. Let's multiply all the x values by -2. And let's add 3 to all of our y values. If we then plot these couple of points that we've got, let's see how it looks. 4, 1 comes up here. 0, 2 comes up here. And -2, 4 comes up here. So let's reconnect them. This segment here is a straight line, I can tell. This one's got a little curve to it, so I'm going to try to keep that curve going. I don't know. Looks okay to me. Kind of looks like you got some person relaxing on a recliner there. Oh yeah, I'm having such a nice time with the reflections. Yay, we're so happy. There we go. And if you did want to do manual movement of the points, let's just track this random one here. Let's reflect it first over the y-axis. Boom. Temporarily right here. Okay, let's now double the x value. This x value is 2. If we double it, we get 4. And then if we slide it up 3 places, you do see it aligns nicely with what we've already seen. Okay, Honors Algebra 2. We're going to try to slide through these next 2. And hopefully I've not lost too many of you. I did try to pre-write out the transformations just to cut the time of the video down. Again, if you need to pause to catch up, that's what you gotta do, no problem. But number 4, outside vertical. We're gonna multiply all the y values by 5/2. That's gonna make them bigger. Vertical expansion by 5/2. Inside, right by 3. Move all of the x values right by 3, which will increase them by 3. And I did already do some pre-writing to just show our plan here. Let me do the multiplication in the y column. And my thought, as always, will be if we can just plot these new points, we should witness the transformation take place that we have already described. And again, verify with your eyeballs. Is the graph about 2.5 times bigger? 5/2 times bigger? Why, yes, it certainly is taller. And has it moved right by 3? Again, yes, visually, it does appear that that happened. And the manual movement of the points would get you the same effect, though I'm going to not show it every single time just to save some seconds in the video. Okay, our final one here, number 5. Here's our original f of x. Looks like a little seahorse. I'm going to name it Seahorse. And our transformation, there's 2 things we've got to do. We do notice they are factored away from each other. That's ideal. That's why I put the heart there. So 2 multiplied by x inside horizontal opposite, we would divide the x's by 2, which is the same as multiplying them by half. That's our horizontal compression by half. Separate from that, we would move everything left by 5. So after we multiply all the x values by 1/2, we will then subtract 5 from them. There are no vertical transformations of this little seahorse, so I'm not going to do anything to the y values. They'll stay the same. But yes, every x value I multiplied by half and then added 5. And let's see how this goes. -6, 2. -5, 3. -4, 0. And -3, -3. So yes, visually we can tell our little seahorse has moved left. We could also tell our little seahorse is a lot thinner than it used to be. So that's all I've got to say about that, Honors Algebra 2. I hope you've enjoyed this little video. I'm going to scoot on out of here. Please scan and upload this to Teams by the deadline. Ta-ta!